Um, Hi, everyone. Welcome to my talk. It's about kernel alchemy, crafting mobile kernel code to evade modern RASP solution, right? So, yeah, without further ado, want to introduce myself. So I'm Subho Halder. I'm co-founder of AppNox. AppNox is into mobile application security platform where you can perform assessment in an automated fashion. I'm a mobile security researcher for more than a decade now, and I've been giving trainings and been speaking at Black Hat, DEF CON, RSA, NullCon, and many various other conferences related to mobile app security. One of the famous vulnerability which I kind of figured out was CVE 2013-0926. That's regarding RCE using WebKit, and we were able to find out, run remote code execution on applications which were using WebKit. So that's enough about me. Let's move on. A quick introduction about what mobile RASP landscape kind of looks like, right? So the mobile security has evolved more than rather basic checks of root detection, emulator detection, right? And RASP became a category because it is evolving. It is trying to attack the evolving threats, which is upcoming, the advanced defenses which RASP brings into it, and obviously the ongoing arms race between defenders and attackers, right? So that's the kind of a RASP landscape kind of looks like. And to understand what are the technologies RASP is bringing into the table, we need to understand how it works. It works by integrating itself during an application development or deployment cycle. It does our runtime monitoring of how the application behaves and understand the inputs and the system instructions. It understands threats and tries to prevent it. And it also gives you an automated response to those threats by taking immediate actions like closing the application or throwing an error message, right? Some of the common RASP protection mechanisms are obviously emulator detection, root detection, hooking detection, right? But what now the newer modern RASP brings into the picture is integrity check to understand if the application has been tampered with in the memory space or not. And it verifies the authenticity and the integrity of each and every app component, right? So what are some of the challenges in evading RASP? Now, if an application which has RASP integrated, the problem with tools and manual pen testing is, one, these applications are obfuscated. It becomes a little bit difficult to actually go ahead and decompile these applications and figure things out. Two, these application has dynamic checks inbuilt, so it becomes a little bit difficult to hook using tools like Frida or application instrumentation stuff. So runtime monitoring adapts to this, becomes a little bit difficult. And third, it is a multi-layered approach. It is not like one-time bypasses, but there are continuous check which happens when the application is running, right? So these are some of the challenges while you're trying to evade RASP detection. So before we proceed further, let's talk a little bit about how the Android kernel looks like. The reason is all of these detection mechanism or all of this RASP mechanism, how RASP detects, can be actually bypassed using kernel. That's the highest level of trust and privilege which you have, right? So before we talk about it, let's take a quick sneak peek into how the Android kernel looks like. In this talk, I'm just going to cover Android. But our team has done a lot of research in Android and iOS as well, but over here we're going to focus on one, right? The architecture is pretty simple. It is based on Linux kernel. It is open source. You can go ahead and download these kernel files. You can search in GitHub. It's pretty easy to figure out. And for this talk, we are talking about OnePlus phone. So OnePlus 6 is the device which we took it for our R&D purpose. And we download the kernel, which is open sourced once again. And how this driver framework kind of looks like. On the right-hand side, I know it's a little bit difficult to see, there will be a folder called drivers, and that's where all the kernel drivers are written. And you can actually write your own custom kernel drivers and compile it, and you can interact with the kernel functionalities over there. And on top of that, there is something called syscall, and that is exactly what we're going to talk a lot about. What is the syscall? Syscall is basically an interface by which the user space application or the user space can interact with the kernel space. And that's the communication happens via syscall, right? So like moving a file from one directory to another directory, that the user space sends out that signal to the kernel space saying that, hey, I want to move this file from here to here. The kernel does that. So that the communication from the user space and kernel space happens via syscall, right? A little bit about how these syscall work, right? So system calls or syscalls provides a way or an interface to speak between these two interfaces, these two spaces, right? In Linux, these are defined in include/linux/syscall.h. It is available online. You can go through it. And the entire syscall table is present in arch that / your architecture, ARM64, Intel, or whatever, /tools/syscall.tbl, right? To give you a little bit of idea how it kind of looks like, if you look at it, there are syscall like sys_getcwd, which is current working directory, or sys_mkdir, that is to make a directory, right? sys_chdir, that's changing directory. So whenever you type this command in your terminal, it basically calls a syscall in the kernel, and the kernel does the thing for you, right? So you get all of this syscall table in the /tools/syscall.tbl. The screenshot is from the OnePlus kernel syscall table file. It is again available in the open source kernel, right? So the question is, can these syscalls be invoked directly? Because generally what happens, these are abstracted. These are very low level, right? So these are abstracted via libc or via some other methodology by calling the syscall, right? So for example, this is a sample code. If you look at it, this is an assembly code. You can write this in a .asm file, compile it, and this is how you can actually directly call a syscall. The example over here is this piece of code checks the existence of the file example.txt, and how it does is, if you look at it, the syscall for f-axis at, that's the syscall which we're going to use to figure out if the piece of file is available or not. And the number is 48, depending on the kernel. And how we do is, we call this syscall using svc, right? And we are invoking the syscall, making sure we are putting the correct values in the registry, and we can see if it is success, it will return 0, and then if it is a fail, then it should return 1 with an exit status 1, right? A very simple kind of assembly level language which you can actually write to figure out how you can directly call a syscall. Now, instead of doing this, you can also write a Java code saying that, hey, os.copy, or Python code os.copy to some other place. That's also fine, but internally, it still uses syscalls to do that, right? All right. So in this example, instead of example.txt, we can actually replace this with, for our mobile use case, with frida-server or whatever those specialized system calls which is required. And we can actually monitor, Frida in that case, or any instrumentation framework cannot actually figure out what kind of syscall this is or intercept it in a good way, right? Frida and all of these instrumentation thing works on top of user space. And when you write it in an inline kind of a function where you call syscalls directly, it is very, very difficult to actually intercept it or to block it. And that's exactly what most of the RASP provider does. All right. I know this is a long slide. You can take a screenshot of it. But these are some of the tactics RASP companies use, right? These are mostly the 5 tactics, right? Number 1 is it does a root detection not only through the Java part of it, but through the native part of it by doing a syscall. One of the examples I gave you in the previous slide, using if-access at to figure out if these files are present or not. Second, it does a port scanning strategy, because when you're running Frida, Frida opens up a port internally, and it does a port scanning. Usually it's 27042 is the port which opens via Frida. but sometimes you can change the port. Some RASP solution does a full port scanning to figure out if there is a Frida server or a Frida gadget running behind the scene. Third is it also looks at /proc/tasks to figure out what are the different tasks which are running in the system. It figures out if gum.js or Frida server or gmain or all of these name of the tasks are running. If it runs, then it kind of blocks it. Again, all of these are via syscalls, right? It also does memory integrity check by looking at the libraries which are loaded and looking at the ELF headers and figure out what are the checksum it is using. And again, it uses /proc/pid/maps to figure out where all these libraries are loaded, right? And the last thing is obviously it also scans for a list of hacking or tampering tools like Riru, Magix, Expose, etc., scanned in the syscall as mentioned above, right? So these are some of the things which the RASP vendors kind of use in a broad 5 categories, right? So the key component for security evasion, we need to bypass these 4 things basically for any kind of RASP solution, right? One is they do a memory management in terms of they control the system memory, looks for integrity checks in that. Can we bypass that? That's number 1. Number 2, it does a networking stack. It kind of observes what are the different ports which are open, what is running in those ports, kind of handles communication relevant for blocking security scans for those ports. Third, file system. This is easy. It manages data access, important for hiding security tools and artifacts. So for jailbreak, there will be artifacts which will be there in the file system, but it uses the file system syscalls for that. And obviously, the 4th one is the process management, where it oversees running applications key for disguising as a security tool, right? These are the 4 things generally which is used. Now, to understand how we need to write this kernel modification tool, 1, we need to get the kernel source code, of course. 2, we need to cross-compile this for your device, for your specific device, right? Third, we need to use something called an Android kitchen. We are focusing on Android in this talk. This assists you in packing and unpacking the boot image for modification of your kernel, because that's where all of your code is going to stay. And 4th, obviously, you need ADB and fastboot to communicate with the device, right? Yeah. So that's about, and how do you set up your development environment? You basically download the cross-compilation tool chains like Clang or GCC. You configure your build system. Make sure you prepare your make files and configuration files for your target, and obviously set up some debugging tools to debug your kernel piece of code which you have written. Because it's very important that if you write buggy codes for your kernel, your phone is going to hang and freeze, and it can become bricked as well, right? So how do we write the custom kernel driver, right? Custom kernel drivers are essential for intercepting and modifying specific syscall. You can actually write your own syscall, or you can actually redirect the existing syscall into a different one, right? So we need to write a kernel driver. The objective is we need to write a kernel driver to intercept the following syscall and modify them and their parameters on the fly, right? 1 is the sys_connect syscall. 2 is sys_bind syscall. 3 is sys_read syscall. sys_faccess add syscall, and open add syscall, right? So these are the 5 general syscall which we need to try to have a replacement of, right? We can also hook ptrace as a syscall, but we are not going to go into that. That requires a little bit of more, hand-holding work on top of that. But remember, the main important point which I've written at the bottom is a frozen kernel is a major problem. So make sure your driver functions are efficient and avoid overloading kernel, because they do not have a lot of memory in general, right? So what are the interception techniques, right? 1 is you can directly modify the syscall table because you are compiling the kernel itself. You can just go into the kernel, like before you compile the kernel, you can directly modify it. Or second, you can use ftrace-based interception, where you do not modify the kernel per se, but you have a kernel tracing facility to hook into the syscall and redirect it to your custom written function. Third is like a kprobes, where you can dynamically instrument the kernel function. It's similar to how Frida works, and you intercept it, and then you change it on the fly. Or fourth, which is very important, which a lot of cloud providers uses, are like eBPF programs, where you can attach custom code to certain kernel events as well, right? In this talk, we are going to focus more on ftrace-based injection, because that's what we were able to work on. So yeah. So so now what we need to do is we need to implement a syscall relocation, right? Because it should not go to the actual syscall, it should relocate to my piece of code and then go back to the actual syscall, right? So how do we do it? First, we need to locate the syscall table address from your kernel. Second, you need to back up the original syscall, of course, because you're not going to make every syscall go through your custom code, but you need a backup of the original. Third, you need a replace function to replace that syscall with your own custom syscall. And fourth, obviously, you need to handle this call to make sure that it works, right? So this is the basic steps which is required to make sure that you are writing a proper kernel driver. And in textual, this is how it kind of looks like. So different RASP mechanisms require tailored evasion techniques, right? And you need to understand these specific protection, which enables more effective bypassing strategies. Techniques like root detection, you need to intercept file system check. Technique like emulator detection, you need to modify hardware identifiers. Technique like hooking detection, you need to conceal the memory modification, which Frida or any other such tool does. And fourth is integrity check. You need to return falsified checksum comparisons, which happens over there, right? And I'll just go through each of these techniques a little bit fast so that we understand. So bypassing the network-based detection. So RASP solution often use network-based detection to intercept and modify network-related syscall, and these can be bypassed, right? One is port scanning prevention. As I said at the earlier start of my talk, Frida actually exposes a port, and these application goes through, does a port scanning to figure out what are the different applications that is running in certain open ports. So we need to make sure that we can intercept bind and connect methods in the syscall to hide the security tool from figuring out these ports. Traffic obfuscation, modify the network data itself to conceal that, the banner of whatever the security tool which is running. So if you actually do a telnet to 27042 when Frida is running, it'll give you a specific banner. If you do not want to hide the port, you can change the banner itself in the syscall table, and you can obfuscate the traffic. A third is DNS query manipulation. This is more of external communication. So you alter the DNS request so that it points to your own kind of a DNS, which you can set it up, right? File system level manipulation techniques. I've already shown an example in my previous slide how a syscall is used for a direct file manipulation. So what are the strategies which we can use? One is we can do a path redirection, right? So whenever that syscall is invoked, we can figure out what exactly the path it is trying to look for, and then you manipulate the path to some other path where it doesn't exist. Second, access interception. You probably might want to block the read operation itself and say that, hey, you are not allowed to read. Or third is permission spoofing. It's similar to access interception, where you alter the permission, file permission, so that RASP wouldn't be able to detect the modification which is happening, right? The memory integrity check evasion, this is very, very important, and this is very difficult, actually. So one is, again, checksum manipulation, because RASP solution kind of tries to figure out what is the checksum in the memory of the loaded libraries, and they kind of compare it from the file system and the memory, if the checksum matches or not. So if you can intercept the memory read operation and return a valid checksum, which we can read from the file ourselves and do it. Or memory cloaking, we can hide these different libraries from being loaded by hiding them. Or dynamically patching it, implement on-the-fly code modification that revert these integrity check, right? These are some of the techniques which we can use. So yeah, so how does it work? After you write your drivers and you kind of zero out the techniques which you want, you need to configure your build system, compile the kernel, package this boot image into a boot.img file, and then flash it into your device, right? So let's build our own kernel driver. I'm going to give you some code examples. Feel free to ask questions. But yeah, so what we're going to do is we are naming this driver as OHAYAS, OHAYAS, right? What you can do is you can download any of this kernel tree, GitHub, from GitHub as an open source. Go to your driver, create a folder called OHAYAS, and you can create a file .c. At the end of the talk, I can give you the GitHub link where we have created this as a POC, proof of concept. What we are going to do is we will create an interceptor, relocator for a syscall interface, right? And we will be either using a direct hooking strategy or a kprobe or ftracing hooking strategy. A direct hooking strategy would be directly writing that, hey, please replace this syscall with my syscall. Or a kprobe or ftracing strategy would be to actually probe or instrument the kernel itself, and whenever this syscall is called, instead of actually calling that syscall, call me, right? In this example, we are going to talk about direct hooking because it's pretty easy. Ftracing and kprobes might become a little bit difficult, but a lot of tools exist which can help you do that as well, right? All right, so let's look at the code. I know this is not a coding conference, but still. So this is how the structure kind of looks like of your .c file. So if you look at it, we have some structures, right? These structs are defined as the syscall number, the name of the syscall, and the address, right? And we actually created some boilerplate code for finding a symbol in export, replace function, which is to replace the syscall, a restore function, which is to restore the existing original syscall itself, right? So this is how it kind of looks like. Sorry. Yeah. And in this example, we are doing a direct hooking strategy, and that's why we have written these functions ourselves, saying that, hey, I want to replace restore or get the syscall direction as well, right? So let's go to the next option. Yeah. And the most important thing is about the get syscall address. In this get syscall address, we are trying to figure out where exactly are the syscall table located in runtime, and then replacing those syscall with our own custom implementation. That's the kind of the thing which the code kind of does. Don't worry, this code is available in GitHub as well. So this code is very simple and straightforward. It uses a struct to pass the syscall, which I showed you in the previous slide. Pass the syscall number, name for hooking. The relocator copies the original syscall address, replaces it with a new one where we have written our own implementation of the syscall. The original address is also returned at the end, which may need it if you want to continue saying that, hey, I want to change something, and then hand it off back to the original syscall. So that's how it kind of, you can use this part of the code for your strategy, right? We are next going to create a .h, a header file, which kind of defines the syscall which we are going to hook. Again, if I kind of show you, you can follow my mouse, the old connect. So we are, again, our strategy is to connect to these syscall, connect, bind, faccess at, open at, and read. So we just renamed it as old. This is just to make sure that we have the backup of the original syscall, and we kind of create our own structure, the original structure. And we kind of say that, hey, the old connect, old bind, old faccess at, old open at, and old read are stored in this syscall binary itself, right? And these are some of the things which we are going to search going forward in the slide. This is necessary because we need to execute the original syscall at the return so that we can correctly send the return value. Otherwise, your app or your operating system might crash as well, right? So let's build a kernel driver. This is an example way of actually changing the open at syscall itself. The code which we have written over here is very simple. Over here, what we are trying to see is we are checking what is the PID on which this kernel will be working with, because I don't want to get the overall whole operating system go through my code. I just want one of the process ID to go through my code. So I'm going to check that code, which one is it. And in that, for example, we are going to check, hey, is it a Frida gadget artifact string, which is trying, this open at syscall is trying to, open. And if that is what, we are going to print an alert saying that, hey, Frida gadget detection was done, and then we're going to return it as -1, saying that, hey, we did not find it. Right? We actually do not go ahead and do it. We kind of pause it right there, and we kind of say, hey, -1, hey, we haven't detected that file. Or in case of a Frida folder, we also check if Frida folder is detected, and you can actually keep on expanding this with different other artifacts which you want a syscall not to detect for you, right? And at the end, as you can see, we call the old openat, which we had defined in the previous file, and we pass on the flags and the mode and our different return ID into that, and then return it if there is no other calls, right? So again, just to say, if you want to modify something, we return here itself. But if you do not want to modify something, we will call that old openat function and return whatever the return value the old openat function was trying to return, right? That's as simple strategy as we can do. Very simple, right? Not that too complex. Maybe the coding might be a little bit complex, but the logic is not. All right. Let's go to the next one. And then we need to build this kernel driver, right? Once all of this is done, let's look at how we can compile this driver in the first place, right? We can go ahead with two ways. One, we can make this as a loadable kernel where we can create a .ko file and then load it in runtime, or we can make it embedded in the kernel itself, right? In this case, we did a inbuilt direct compilation because for the kernel of 1+6, we were not able to build a loadable kernel, unfortunately. But this is exactly what we did. These are some of the configuration value which we need to put in the make files to make sure that we can hook the interceptor. And once that is done, we also included this driver to be included in the compilation of the kernel as well, and obviously put the source that, hey, this driver, the source of this driver is right here. So the automake can take it up and compile it for yourself, right? How does it kind of looks like? Once we ran this, right, as you can see, if you remember the piece of code which I talked about for openat, it kind of immediately started printing out that, hey, this application was trying to open this path, right, and so on and so forth, right? The thing is, this application is using one of the modern RASP solution, and we are not hooking into anything in this application. What we're doing is we are talking to the kernel directly, and we're telling the kernel to tell us what are the different file paths it is trying to access, right? It kind of tells you and prints out all the file paths which is there. And as you can see over here, it detects a Frida gadget detection over here, right? And immediately what it does is it immediately returns -1, or if these are the file paths it is trying to open, which is not the file path which we have put in as a signature, it kind of returns or calls the original openat. Similarly, we have done it for f-access at and multiple others in the example which I can show it to you, right? If you look over here in f-access at, we are able to figure out that, hey, expose installer and things like that are being called, but we kind of blocked it in the kernel itself. You're not writing anything in the user space, right? So yeah. Now the most important part is testing and validation. After writing all of this kernel piece of code, you need to thoroughly test your piece of code, because kernel does not have enough memory, so you cannot actually copy files in the kernel space and then modify it. It doesn't have libc as well, so you cannot do a direct string comparison and things like that. So that is why I had to hard code the process IDs instead of dynamically trying to load it. But in the example, in the GitHub example, we actually copied a lot of libc functions internally in the kernel as well, so that we can use it easily. The kernel stability is very, very important. The evasion effectiveness, we have tested it with various RASP solution, RASP protected application, and we can confirm that this bypasses work universally, right? Because at the end of the day, you have the highest privilege if you have access to the kernel itself, right? The performance impact, we have checked the performance impact by utilizing our evasion technique, and it is negligible, because what we are trying to do is we are trying a quick string comparison in most of the checks, and we are actually calling the original syscall at the end of the our modified syscall thing. So that's what it is. But we have seen some edge case and which we had to handle, and we need to make sure that these edge cases are handled in a proper way. We need to ensure robustness against such various RASP implementation and scenarios. But what we have seen is it is kind of impossible for your RASP vendor to actually figure out a way to bypass this syscall directly, because we have access to the kernel and that's what it is, right? Future research in the field of mobile kernel security and RASP evasion, this is a cat and mouse game kind of a thing, right? The moment RASP vendors comes up with a specific way of defending, there is always an offensive way of evading it. And future development will shape both attack and defense strategies as well. This just scratches the surface of what we have done. This is, again, open source. You can explore more on top of it. But this is just the Android. We also have an iOS R&D going on as well, where we are able to hook into the iOS kernel cache and figure things out, where we can bypass most of this protection technique which RAS vendors kind of brings into place. This presentation kind of provides you a groundwork to start off with. So the idea is RASP is not enough for your security, right? RASP can be utilized like a, in terms of internet, it's like more of a gateway, which kind of provides protection, but that protection can always be broken. So it makes more sense to make sure that you write secure code and not depend on only just RASP. So that's the idea of this talk. I'm just going to quickly show the GitHub link which we have over here. And just give me 1 second. The link is in the QR code. I'll just open up the slide, so don't worry about the link. You can get it. So this is the repository of 1+6 for Android 13. As I said, in this repository, I'll just increase the screen size so that you can see. There's a folder called driver. If we recall our presentation, we click on the drivers, and then you will see all the drivers which are there in the Android are part of this. And we are going to go to OWASP. That's the driver which we have written. Yes, this is the driver, right? And this is the C file which I was talking about in my presentation. So if you open the C file, you will see there are different ways of scanning the process, figuring out write, read locations of the process, and you can go through this. I'm not going to take a lot of time making you understand the piece of code. You can actually go ahead and download this repo and create your own kernel based out of this. So that's what it is. I'll just open this slide up so that you can take a screenshot of the QR code. The repo is right over here. You can go ahead, open the drivers, figure it out how it works, right? I'll just take a second for this. There is some more RAS bypass technique. Now, kernel bypasses are really, really difficult. So if you guys are Frida users, and if you want Frida, if you're using RASP, it's pretty easy to actually evade most of the RASP which is there in the market by just modifying few things in Frida itself. One thing which we had released open source in our last conference was Nox Frida Patcher. Again, this is the GitHub repo. It's very simple. It's a Python file, and you just run main.py, your Frida gadget. It kind of tells, or you can just go to the releases, and you can download the patched Frida gadget for Android. And this, almost all the RASP which are there will get bypassed using this Frida gadget. Again, this is all open source. You can look at it. This is a bonus content which I'm giving. The QR code is here. If you want to take a screenshot, you can. We'll give you that. All right. And questions? You can reach out to me at Twitter, or you can scan this QR code for my LinkedIn. Happy to connect. Happy to take questions. Thank you. Questions?